Hello, this is Richard Hammack's Calculus 1 course. We are in part 3 of the course on derivatives. Today, lecture 19, the derivative of e to the power of x. Today's goal is simple. We'll derive a formula for the derivative of the natural exponential function e to the power of x. And when we get that formula, it will become our latest rule in a list of rules for finding derivatives. You'll recall that e is an irrational number approximately equal to 2.718281828, and the function e to the x is called the natural exponential function, and it's graphed here. Like any exponential function, it passes through the y-intercept of 1. Here's the point 0, 1 right there. And like any exponential function with base bigger than 1, it gets large rather rapidly, as you see here. It turns out that the formula for the derivative of e to the x is very interesting and a little bit surprising. And I'll tell you what I'll do. I'll cut to the chase and I'll give it to you right now. The derivative of e to the power of x is equal to e to the power of x. The derivative of the natural exponential function is itself. That's a very remarkable property, a function whose derivative is itself, but it happens with e to the power of x. What we're saying is this: if you take a value of x and look at the point on the graph of e to the x at x, and establish a tangent line, the slope of that tangent line is going to be the derivative of e to the power of x at x, which is just e to the power of x. M is equal to e to the power of x. So if you plug in x to e to the power of x, you go up a distance of e to the power of x. And think about this right triangle here, and its rise over run. If the run is 1, the rise would be e to the power of x in order to give us a slope of e to the power of x. So as x gets big, you can see that this rise over run has a rise that's e to the x. It gets big very quickly, so slope gets big very quickly as x increases. But always at x, the slope of the tangent line is e to the power of x. Given that, think about what happens when x is equal to 0. Let's move x over to 0. The slope of the tangent line to the graph of e to the x at x equals 0 would be m, which is e to the power of 0, and that's 1. So this slope is 1. This is a very interesting property of the natural exponential function e to the power of x. At the y-intercept, 0, 1, the slope of the tangent to the graph of e to the power of x is very simple. It's 1. And it's a fact that f of x equals e to the power of x is the only exponential function that has slope 1 at the point 0, 1. To underscore this fact, think about the graph of y equals 2 to the power of x, the exponential function with base 2, which is smaller than e. So the graph of 2 to the power of x is not quite as steep as e to the power of x. And if you look at the slope of its tangent line at the point x equals 0, that slope is slightly less than 1. On the other hand, think of the exponential function 3 to the power of x. 3 is bigger than e, so this exponential function is steeper than e to the power of x. And if you look at the slope to it at x equals 0, that slope is greater than 1. It's surprising that, as strange a number as e is, it's the exact number that makes the slope to the graph of y equals e to the power of x equal to 1 at x equals 0. So we'll see why that's true today, and we'll use it to help derive the formula d dx of e to the x equals e to the x. But I'll be honest with you, if you are content accepting this formula on faith, you can add it to your list of rules and go on to the next lecture without listening to the rest of this lecture. You'll be fine. But if you're curious about why e has this strange property, where the number e comes from, and how we get the formula d dx of e to the x equals e to the x, then that's what we'll do for the rest of today's lecture. So stay tuned. Today's plan is to, first of all, find a formula for e. Then we'll show the fact outlined here that y equals e to the power of x has slope 1 at the point 0, 1. Using this, we'll show that the derivative of e to the power of x equals e to the power of x, and then we'll look at some examples. So that's today's plan. Let's start with this formula for e. The formula for e is going to look a little unmotivated when you first see it, but then it'll start to make sense when it's examined more closely. The formula is this. Here's the definition of the number e. E equals the limit as n goes to infinity of 1 over n plus 1 to the power of n. N is the value of this limit. Now it's probably easiest to think of this limit in terms of n being an integer that's getting bigger and bigger and bigger and bigger. E is the value that 1 over n plus 1 to the power of n approaches as the integer n increases without bound. And I'm going to illustrate that with a chart. We're going to take values of n that are integers that are going to get bigger and bigger and bigger, and we'll look at the corresponding value of 1 over n plus 1 to the power of n. For example, when n is 1, over here in the second column we get 1 over 1 plus 1 to the power of 1, which is 1 plus 1 to the power of 1, or 2. Whereas if n is equal to 2, we get 1 over 2 plus 1 to the power of 2. That's 3 halves squared, so that's 9 fourths, or 2.25. For n equals 3, I took a calculator and worked out 1 over 3 plus 1 cubed, and I got this number. For n equals 4, 1/4 plus 1 to the power of 4 turned out to be this. And for n equals 5, 1/5 plus 1 to the power of 5 gave me this. Now, we need to let n go to infinity, so it better start getting bigger faster. If you plug in 10, 1/10 plus 1 to the power of 10 is this number. For n equals 100, you'll get this number. For n equals 1,000, this number. For n equals 10,000, this number. For n equals 100,000, you'll get this number. For n equals 1,000,000, you'll get this number. For n equals 10 million, 1 over 10 million plus 1 to the power of 10 million. Do it on your calculator, you'll get this. So you see here that as n is getting bigger and bigger and bigger, the corresponding value of 1 over n plus 1 to the power of n seems to stabilize at some number around 2.71828. And in fact, if you let n go to infinity, the expression 1 over n plus 1 to the power of n equals a number in the limit, and by definition, that number is what we call e. E equals the limit as n goes to infinity of 1 over n plus 1 to the power of n. It's approximately equal to 2.71828182845, as we can see here. So this is the definition of e, but it probably raises more questions than it answers. It gives us a concrete way to find e, but it doesn't tell us why this is such an important number. Why do we get this strange number? Well, I'm going to convince you in the next slide that for this value of e, this number e, y equals e to the x has slope 1 at the point 0, 1, just as we mentioned previously. That if you define e in this way, and you get this value, when you look at the graph of y equals e to the power of x, and at the point x equals 0, the slope of the tangent at that point is 1. And e is the only base of an exponential function that has this property. So we're going to see why that's true on the next slide. But first I want to take a look at this red tangent line. Its y-intercept is 1 and its slope is 1. So if you look at that as an equation, it's the graph of the equation mx plus b, where m is 1 and b, the y-intercept, is also 1. This is the equation y equals x plus 1. And that'll be important for us on the next slide. So on the next slide, let's take the picture that we have here. It's a little bit bigger. Here is the line y equals x plus 1. And here's the point 0, 1, where it hits the y-axis. Our objective is to show that the graph of e to the x is tangent to this line, y equals x plus 1. That its graph touches the line at exactly one point, right here at 0, 1. And we're going to show this in stages. We're going to begin with not the exponential function e to the x, but a different exponential function. Think about the table in the previous slide. The numbers in its right-hand column had the form 1 over n plus 1 to the power of n for an integer n. Take one of those numbers and form the exponential function, that number to the power of x. It would look something like this. Its y equals the number 1 over n plus 1 to the power of n, that to the power of x. So here n is just an integer. Just pick your favorite integer and plug it in there. Get this base, 1 over n plus 1 to the power of n, and then raise that to the power of x. And that's your exponential function. And remember that if n is big, this base, 1 over n plus 1 to the power of n, that's pretty close to e, but it's not exactly e. So this graph is an exponential function that's not e to the x. It's some other exponential function. So you're probably expecting it not to be tangent to the graph of y equals x plus 1. In fact, you can see here that it crosses this red line, x plus 1, in two places. One of them is easy to find. At x equals 0, these two graphs intersect. They both give a y value of 1. If you plug in 0 to y equals x plus 1, you get y equals 0 plus 1, which is 1. And if you plug in x equals 0 to this exponential function, you have this base to the power of 0, which is also 1. So the two graphs intersect at x equals 0. But they also cross at a different point, right here. And if you think about it, you can see what x value that is. It's 1 over n. Now if you take 1 over n and you plug it into y equals x plus 1, you're going to get 1 over n plus 1. But also take x equals 1 over n and plug it in right here to this exponential function. That 1 over n would multiply times this exponent of n and just give you a power of 1. And then y is equal to 1 over n plus 1 to the power of 1, which is 1 over n plus 1. So these two graphs, this straight line and this exponential function, intersect at 2 points at x equals 0,
and also at 1 over n, where n is whatever integer you choose it to be. So that's our first observation. The graphs of y equals x plus 1 and y equals 1 over n plus 1 to the power of n to the power of x intersect at x equals 0 and x equals 1 over n at 2 points. So the exponential function y equals 1 over n plus 1 to the power of n to the power of x is definitely not tangent to the red line, y equals x plus 1. It intersects at 2 points, here and here. Now the exact function, the exact exponential function that I graphed here, it just so happens to be the one for where n is equal to 1. This is the graph of y equals 1 over 1 plus 1 to the power of 1 raised to the power of x. And 1 over 1 plus 1 to the power of 1, that's 2. So drawn in black here is the exponential function y equals 2 to the power of x. And when you plug in 1 to that, you get 2 to the power of 1, which is 2. And sure enough, that's 1 over 1 plus 1. What I want to do now is think about what would happen if you change the n here from a 1 to a 2. This base would change to 1 over 2 plus 1 to the power of 2. And that's raised to the power of x. Let's look at that. Here we go. It looks like this. We have a new exponential function, y equals 1/2 plus 1 squared to the power of x. And from our observation, this exponential function crosses the line y equals x plus 1 at 2 points here and here, at x equals 0, and also at x equals 1 over n, which is 1 over 2 in this case. So now let's increase n from 2 to 3. So this base is going to become slightly larger. We have y equals 1 over 3 plus 1 to the power of 3, whole thing to the power of x. And the graph of this exponential function crosses our red line at x equals 0 and x equals 1/3. Now let's increase n from 3 to 4. We get y equals 1/4 plus 1 to the power of 4 to the power of x. And its graph, the graph of that exponential function, crosses our red line at x equals 0 and x equals 1/4. Increasing n to 5, we get a new exponential function. It crosses the red line at 0 and 1/5. Here is n equals 6. Y equals 1/6 plus 1 to the power of 6 to the power of x. Crosses at x equals 0 and 1/6. And here we want our n values to get bigger, so let me jump from n equals 6 to n equals 10. So here's the graph of y equals 1/10 plus 1 to the power of 10, all to the power of x. And it crosses the red line at 2 points, they're very close together, at x equals 0 and 1/10. Now from n equals 10, let's jump up to 20 now. Here's the graph of y equals 1 over 20 plus 1 to the power of 20, whole thing to the power of x. And it crosses the line y equals x plus 1 at 2 points, here and here. They're very close together. One of them is at x equals 0, and the other is at x equals 1 over 20. You can see here that this exponential function is almost tangent to the graph of y equals x plus 1. But not quite. It goes under that line just a little bit and crosses 2 times at 2 points very close together rather than one single point. The observation I want to make here is that the bigger n gets, the closer and closer this exponential function is being tangent is to be in tangent to the line y equals x plus 1. Because the bigger n is, the closer together 0 and 1 over n are. 0 and 1 over n, the closer together they are. So the closer y equals 1 over n plus 1 to the power of n to the power of x is to be in tangent to the line y equals x plus 1. The bigger n gets, the closer and closer this exponential function is to be in tangent to this line y equals x plus 1. So if it's true that the bigger n is, the closer this is to be in tangent to the red line, then just let n get bigger and bigger and bigger. Let n approach infinity. Think about the graph of y equals the limit as n approaches infinity of 1 over n plus 1 to the power of n, all to the power of x. There, these 2 points, 0 and 1 over n, approached each other, the 1 over n approached 0, and we get just one intersection point. So the exponential function y equals this limit to the power of x, you'd have to conclude that's tangent to the graph of y equals x plus 1. But the limit as n goes to infinity of 1 over n plus 1 to the power of n, that was our definition of e. So this is y equals e to the power of x. And you can see here that it is tangent to the line y equals x plus 1. That's our inescapable conclusion. That the line y equals x plus 1 is tangent to the graph of y equals e to the x. So that was one of our goals. In fact, what we get from this is that if y equals e to the x is tangent to this line y equals x plus 1, which has slope 1, then the slope of the tangent line to e to the power of x at the point x equals 0 would be the slope of this red line, which is 1. So therefore, the graph of y equals e to the power of x has slope 1 at the point 0, 1. This was one of our goals. We said earlier that the exponential function e to the x is the only exponential function that has slope 1 at x equals 0, and we've just proved that it does have slope 1.
We'll move on to our next goal. We wanted to find a formula for the derivative of e to the power of x. So to do that, let's let f of x equals e to the power of x. And the question we're trying to ask is, what is f prime of x? Now, in doing this, we'll use the definition of the derivative to get an answer. But in so doing, a certain limit is going to pop out, and I want to tackle that limit now in this box. And I'm going to label this a useful fact. On the previous slide, we showed that the slope of y equals e to the power of x at the point 0, 1 is equal to 1. We just showed that. But now think back to our formula for the slope of a tangent line to the graph of a function f of x at x equals 0. It was the limit as h goes to 0 of f of 0 plus h minus f of 0 divided by h. That's from several lectures ago. That's a formula for the slope of a tangent line at x equals 0 to the graph of f of x. And here our f of x is e to the power of x. So this limit is the limit as h goes to 0 of e to the power of 0 plus h minus e to the power of 0 over h. And e to the power of 0 is 1. And e to the power of 0 plus h is just e to the power of h. So we have here the limit as h approaches 0 of e to the power of h minus 1 divided by h. In this box, in this chain of equalities, we see that the value of this particular limit is 1. And that's going to be useful in computing the derivative of e to the power of x. And let's do that now. The question we have here is, what is f prime of x when f of x is e to the power of x? Let's find out by using our definition of f prime. The definition of the derivative f prime of x is the limit as h approaches 0 of f of x plus h minus f of x divided by h. And here our function f of x is e to the power of x. So f of x plus h is e to the power of x plus h. And the f of x here is just e to the power of x. So we get this. And the term e to the power of x plus h that's right here, using a rule for exponents, you could write that as e to the x times e to the h, because after all, the exponents add and give you this. So we have the limit as h approaches 0 of e to the x, e to the h, minus e to the x over h. The two terms in the numerator have an e to the power of x in them, so we can factor that out of the numerator. In this limit, it's h that's approaching 0. That's the variable in this limit. X is just a number. You could think about x as an unspecified constant if you wanted to. So because this is the limit as h goes to 0, this e to the x can be treated as a constant. You could take that outside of the limit, and we get e to the x times the limit as h goes to 0 of e to the h minus 1 over h. So we get this limit here that's exactly the limit that we have up here that we said was equal to 1. So in working out our f prime of x now, we get e to the x times the value of this limit. That's e to the x times 1, and that's just e to the x. So there we have it. We've just computed f prime of x. We've answered our question. When f of x is e to the x, f prime of x is also e to the x. We've justified our rule for the derivative of e to the power of x. It's equal to e to the power of x. This is our new derivative rule. A new formula. So this was on our list of goals for today. This is in fact, our major goal. We have a derivative formula for e to the power of x. E to the power of x has a derivative equal to e to the power of x. So let's look at some examples. In conjunction with our other rules for derivatives, we can now compute more types of derivatives. For example, if we had d dx of 5 times e to the power of x, the constant multiple rule says that's 5 times the derivative of e to the power of x, or just 5 times e to the power of x. If we have the derivative of x cubed plus 5 e to the power of x, we can use the sum difference rule combined with the power rule and combined with our new rule to get this as the derivative of x cubed, which is 3x squared, plus the derivative of 5 e to the x, that's plus 5 e to the x. So there's our answer. We get it in just one step. What about the derivative of e squared? Be careful here, because we're not saying the derivative of e to the power of x, which would be equal to e to the power of x. This is e to the power of 2. Now, e is a constant. It's 2.7 approximately, and you're squaring that, so you're getting a number around 6 or 7 here. E squared is a constant, so its derivative is going to be 0. To underscore that, here's the graph of e to the power of x. It's a variable function. It increases with x. But if you graph y equals e squared, that's just a straight line, a horizontal line, whose y-intercept is the number e squared. And all of those slopes are 0, wherever you are. So the derivative is equal to 0. So it makes sense. So that's it for today. The takeaway is we have a new formula for a new derivative rule for the derivative of e to the power of x. In the next lecture, we're going to come up with additional rules. We'll have what's called a product rule that's going to tell us what is the derivative of a product of two functions, and also a corresponding companion quotient rule, which tells the derivative of the quotient of two functions. So that's next time in lecture 20. I'll see you there. Goodbye.